Good morning, everyone. I hope you're all fine. Two presentations on distributed self-organization. What is self-organization about? What you can see over here is a little simulation of pedestrians. You can see that in all those 6 different versions, pedestrians behave differently. We do see that they self-organize. There are different kind of patterns. The difference is that parameters have been changed just a little bit. So small changes can make big differences. We're talking here about complex systems, complex dynamical systems, in fact, and there are many of them in the world. Turbulent fluids, traffic flows, large supply chains, social, political, economic and ecological systems, financial markets, group dynamics, and so on. And one of the characteristics of many of those systems is that there are limits of predictability. The reason for this is known. Even if we had 1,000 times or 1,000,000 times more measurement points, more data, we could not really predict the weather for a year, for 10 years or 100 years. Because what happens behind this weather dynamics is turbulence. And turbulence is a phenomenon known from physics where basically small changes can really make a big difference. Now, here is an experiment that shows basically what happens if you increase the flow rate of a fluid in a pipe. So usually there would be laminar flow, but if you push water too much, then it starts to become unstable in its flow, and eventually there would be a turbulent flow. We have similar kinds of phenomena in, for example, the Lorentz attractor. And you can see over here, these are just 3 coupled differential equations, nonlinearly coupled differential equations, and they produce really a very funny dynamics, as you can see over here. What is depicted is a so-called strange attractor. And this example is suited very well in order to illustrate the butterfly effect. The butterfly effect is so funny and so unbelievable, there are even cinema movies about that. So what is it about? It's basically saying, in such kind of a system where we have deterministic chaos, even the slightest change would eventually make a big difference. So you can see over here 2 trajectories, they start basically at the same point, not exactly though, and for a long time those trajectories develop in a parallel way. Eventually, however, they will depart. And that creates this funny situation that in principle, you know, the flapping of the wings of a butterfly could create a storm a couple of months later on. It's hard to believe, I know, but mathematics suggests that such a thing should exist. And to make it even more astonishing, I show you a mechanical system which is really behaving in a deterministic way. Which is a double pendulum. And if you look, what happens is, it's really astonishing. We have actually 3 double pendulum. They're starting at very similar original locations. And for a long time, you don't even see the difference. Now it's eventually departing from each other, but still those pendula behave in a parallel way. Not anymore. And this goes on forever and really creates a very disturbing kind of phenomena, I would say. Another example is the Lotka-Volterra system. It's a well-known model basically for predator-prey dynamics, the simplest ecological system of two species you could think of. And let's assume that we have foxes and rabbits, and somehow there's a hunter who is responsible for taking care of the ecological system. And say the optimal ecological equilibrium would be this point over here. So the hunter will start interfering with that system to aim for that point, that red cross over here. But what happens instead is the system moves to another point. So as you try to control it, in a sense you lose control. You don't achieve your goal. So these are just some surprising observations made for complex dynamical systems. Complex dynamical systems are a daunting class of problems. They are systems with a large number of interacting system elements that can be individuals, can be companies, can be countries, can be cars, can be many things. And those system elements would interact in a nonlinear or in a networked way. And that can create some so-called rich system dynamics, different kinds of dynamics, often pretty surprising. Those systems behave dynamic typically rather than static, probabilistic rather than deterministic, and often in a surprising or even paradoxical way, such as a slower is faster effect. They're often hardly predictable, seemingly uncontrollable, and in a sense a nightmare for politicians and managers of companies and even scientific teams. Now, we need to distinguish complex and complicated systems, really, because many people mix them up. What you see on top is a complicated system. A car is made up of many parts. But those parts are interacting in a way that makes the car well controllable. Otherwise, you would not pay a lot of money for a car. However, if many cars interact on a street, like a freeway, then uncontrollable dynamics occurs. Congestion patterns emerge. That means something that nobody really wants. And so, how can we understand that? This is a well-known example. You've probably seen it 1,000 times already in the summer school. Anyway, everyone here is well educated, has a driving license, right? Has modern technology, clear, plain sight. It's not a difficult task to move steady and avoid an accident. And nobody wants to cause congestion. But this is what happens. How could it happen that something occurs that nobody wanted to happen? We call this systemic instability. And the reason is, if the density is above a critical value, then basically, when there's a little variability in the speed, the next driver will respond, but with a delay. And to make up for that delay, that driver will brake a little bit harder, and the next one even harder. And so there is a chain reaction, and at the same time an amplification effect, and the result is a standstill. The traffic jam occurs. Once you have it, cars flow out in the front, join the queue in the back, and this makes basically the queue move backward. So we can understand all the detail of this phenomenon, but nobody wants it to happen. It's systemic instability, and similar kinds of phenomena happened all around us in the world, and basically, managers and politicians are really struggling with those. So we need to understand them better. And most people try to fight them, to eliminate them, and it's not a good idea. Now, in network systems, things get even more complicated. Rather than the intended effect, you often have side effects, you have feedback effects or cascading effects. So, we typically look at a bunch of people in the way that, oh, this person has this character and that person has that character, so altogether this group should have kind of this combination of characters. This will not allow you to understand group dynamics at all, because there are interactions between those characters, right? And those interactions will make people change their behavior. And so it's the interactions which basically determine the outcome of this. And the stronger the interactions, the more important is the network of people as compared to the properties of the individual. That means if we switch on kind of those interactions, in the beginning it's the individual personality that matters with no interaction. But if we switch on the interactions, then eventually it's the network that takes over what happens. And people are not sufficiently aware of this. Now, we are living now in a time of big data. We can do evidence-based decision making. Still, it seems like we are losing more and more control. And how is this possible? We have better technology than ever, more data than ever, and we're losing control. The reason is that the data volume grows faster than processing power. That means we cannot process all the data we produce. The fraction of data that we will never be able to process is even increasing over time. I call it dark data. That means you need to know what part of the data you need to process in what way, otherwise you get lost in all that data. Moreover, as we network the system, there's a combinatorial growth in the potential complexity of the system. And that overtakes even the exponential growth of, for example, processing power. That means as we try to control these systems in a top-down way, we lose control. And that's why we need a new control paradigm. We need to move from top-down control to distributed control. And for this, we need to understand how self-organization works, because self-organization is basically the secret recipe for distributed control. If you think now we have big data and AI, and those monstrous AI systems with billions or even trillions of parameters will just do the job for us, we don't need to care anymore. Unfortunately, you're wrong. Just take the example of the game of life. A very simple cellular automaton, 3 or 4 simple rules to produce that pretty surprising and interesting dynamics. If you use an AI system and let the system learn the behavior, it will start imitating that behavior, but say with a million parameters or a billion parameters, while actually this model has just, say, 3 parameters. It will have difficulties to reconstruct the original rules that produce that complex dynamics. It will waste a lot of energy on emulating that dynamics. All right, so complex dynamical systems tend to self-organize, and the outcome is resilient to reasonably small perturbation. This is another interesting point. So if you have a stable outcome, then a little bit of change doesn't matter. Chaotic systems are, of course, in that sense, not such stable systems. Here we have instability in certain directions, and that's why we have the butterfly effect. Now, importantly, our brain, our immune system, ecosystems and societies are all complex, dynamical, self-organizing systems. So living systems, the wonder of life, they're all based on self-organization. There's no central data center or processor that controls your brain, your immune system, or whatever. This is all based on self-organization. And it creates wonderful things, you know, how wonderful life can be. Just think of that, you know, how wonderful things our body can do. And a lot of it is based on self-organization. How wonderful things our brain can do. Also, self-organization. So we don't want to eliminate that. We shouldn't. We shouldn't try to centrally control those systems, I think. Now, self-organization also matters for traffic flows. The congestion patterns, and some of them can be understood as emergent patterns, so-called phantom traffic jams, if there's no bottleneck, for example, but density goes across a certain threshold, then we have the kind of dynamics I showed you on that circular road experiment. Here is a video that I recorded many years back in Cairo, and it shows the emergence of a stop-and-go wave. We'll see it move backward. Now it's there, and it's not caused by a traffic light. There's just this on-ramp over here. There's a little road that leads into that freeway that produces small perturbations and triggers basically the stop-and-go wave, but it's not a controlled stop-and-go dynamics. Okay. And even more surprisingly, there are so many different kinds of congestion patterns. These are just particularly difficult examples, and there are also some accidents involved over here, for example. To be honest, you know, if we had started with this data, I would probably have changed the field to do something more simple. At that time, we already had traffic models. We had to show that we were doing a good job understanding the phenomena. What did we do? We basically try to identify elementary congestion patterns, such as physicists were trying to identify elementary particles and make up everything. And we found localized clusters, moving localized clusters. We found stop-and-go waves. We found oscillating congested traffic, and we found homogeneous congested traffic. And then, of course, the question is, with so many different things can happen, when would what kind of traffic congestion happen? Can we understand that? And in fact, we came up with computer simulations of a freeway with an on-ramp. And we were able to produce patterns that look pretty similar to what I showed you before in empirical data. So here again are the empirical data. And we were able to come up with a so-called phase diagram. Phase diagram here shows basically what kind of traffic is expected according to theoretical considerations when there's a certain upstream flow on the freeway and there's a certain inflow over the ramp, or bottleneck strength. That's the capacity that the cars take away that come from the ramp. And the sum of both determines the downstream flow of a freeway with an on-ramp. So we find that over here there would be free traffic flow, and there would be a line above which there would be congestion. And as you can see over here, there are certain equations that determine those separating lines. What makes things even more interesting is that things depend on the size of the perturbation. This is what we get if you have a small perturbation. That's what we get if you have a large perturbation in traffic flow. So there are additional states, the moving localized clusters and the pinned localized clusters, and also the congested area extends. And so if we don't know whether congestion was caused by a small or a large perturbation, we have an overlay of both phase diagrams. So there are areas where several things can happen. Well, this is called history dependence, or hysteresis, or multi-stability. And so really, traffic flow is amazing. And you do all this even without knowing what you do. Right? Still, we can understand it scientifically. Of course, then we were trying to compare it with empirical data. And this is what we found. And you can see that, yeah, there are moving localized clusters in a certain corner of this phase diagram, and pinned localized clusters are together, and oscillating and stop and go is up there. And there are some areas where there could be congestion or free flow. And of course, if we have the choice, we would like to have free flow. And how do we get there? Now, furthermore, we were then considering actually that the outflow from congestion patterns is not exactly constant, as some work of Boris Kerner suggested, but it depends on the weather conditions. So then we scaled the flows by the outflows that were measured on those days. And you can see on some days it was raining, and other days it was dry road conditions. And with that scaling, we see an even clearer pattern in the empirical data, which matches very well these theoretical predictions. So altogether, we can say there is an analytical theory of traffic flow that allows us to understand the complex dynamical phenomena that occur in traffic flows, even though there's so many of them. Some people also call it traffic physics, but of course that's perhaps a bit too restrictive. And we can even calculate the extension of congestion and the delays that are caused. So congestion is largely predictable. Just the moment when it starts is hardly predictable, because it may depend on an overtaking maneuver of two trucks, and we don't know when that is going to happen. So there's some elements of unpredictability, but also a large amount of predictability. And we have to be able to cope with both. Now, pedestrians. Who knows this intersection over here? Yeah, it's a really amazing traffic intersection. I've been there as well. And yeah, pedestrians also do interesting things. In particular, they also self-organize. And most people are not aware of that. They tend to walk here on the right-hand side. In other countries, such as Japan, they tend to walk on the left-hand side. But they do form lanes of uniform walking direction that are segregated from each other. And I've observed that in many different cities, the lane formation phenomenon, and can be simulated, and you've probably seen that also many times. And I was working on that already many years back. I don't even want to let you know how many years back. I still find it fascinating. There are many different models that can produce this kind of phenomenon, but one of the most used one is the social force model, and there are many variants of this model. It basically consists of two equations, an equation of motion and an acceleration equation. And the important point, which makes it basically a force model, is that the acceleration is assumed to be approximated by the superposition of different forces. One of them would describe the adaptation of the actual velocity to a desired velocity in desired direction of motion within a certain relaxation time. And there would be interaction forces with other pedestrians and with walls, and also random effects, of course. And this allows to understand not only the lane formation, but also oscillatory flows at bottlenecks. So basically, while one side is moving through that bottleneck, on the other side, more and more pedestrians aggregate, and they start pushing more and more towards that door, stop that through flow, and then the tide turns, flow direction changes, and so it goes back and forth based on pressure that builds up and is relieved. It's a self-organization phenomenon. While in many situations self-organization works nicely, however, in some situations it can cause disasters. Crowd disasters. Sadly, in India, just another crowd disaster happened. I was shocked to hear about that. We know a lot more about crowd disasters, how they happen, and how they can be prevented. And in particular, one of the unexpected observations that we made in a data set that we got was that there was a transition from a smooth laminar flow to stop-and-go flow under certain conditions that we can quantify and understand. So here you can see it a bit better. And in that case, the stop-and-go flow continued for about 20 to 30 minutes. And we can actually understand it also. There are models for that, for the intermittent flow. If there are too many people basically competing for the same empty space for the next step, then you get these kind of phenomena. This is where we formulated the faster is slower effect. People rush to the door, they push, and the result is they evacuate more slowly as compared to if they would keep a distance. We'll see that all of these observations can also be used for good. After those 20 to 30 minutes of stop-and-go flow, there was another transition from stop-and-go flow to a turbulent kind of flow where people were pushed around in all possible directions. The density was so high that they were experiencing forces from other people, unintentionally so, I suppose. And people were falling to the ground, and the equilibrium of forces was broken. Other people fell on top, and that created a crowd disaster. Some people also call it the black hole effect. Once you have a hole in the crowd, in such a dense crowd, then you have this cascading effect. And it can be disastrous. It happened in many places of the world, including Germany. At the Love Parade back in 2010 in Duisburg, for example. This was the festival area. And there were attempts to control the flow by police cordons. It didn't work. It makes things even worse. So rather than gaining control, they were losing control. And you'll see again some crowd turbulence in this movie over here. And this is what basically triggers the falling of people, and then the black hole effect sets in. Game theory. Also, in evolutionary game theory, we find interesting self-organization phenomena. You've all heard, I guess, about selfish root choice. Here's the right man for this. And there is Bray's paradox. So surprisingly, if you add this road in the middle, it will increase travel times, even though you have more capacity, it seems. And so the question is, how can you overcome it? And of course, there are attempts to come up with control systems. But there are also other approaches. So one of my PhD students, Tesher is his name, he was doing an agent-based simulation, and rather than assuming fully rational agents, he looked at different kinds of behavior of those agents, including adding some noise. And it turns out that this actually improves performance of the system. So less rational behavior, less selfish behavior is smarter in a sense for the system altogether. Now also the social force model can actually be formulated as a game theoretical problem, as a differential game. This is work of Serge Hogendorn and Pete Bovey. Unfortunately, Serge is not here. Anyway. We have been looking at those lane formation phenomena, and what I said is that in many countries there's a preference for one side. Over here in Europe, we typically see a preference for the right-hand side, and the question is, why does that happen? And why does it happen that in other countries, such as Japan, there's a preference for the left-hand side? So we've been looking at this problem from a game theoretical perspective. And obviously it's a coordination problem. So there are two players, in a sense. We have two options, two behaviors, two strategies, either go left or go right. It turns out that if both go left, then they manage to evade each other, right? So there's a benefit of doing that for both, b greater than 0. If one goes left, the other one goes right, they're still standing in front of each other. No success, no payoff, and so on. So basically, this is the payoff matrix of that situation and establishes a coordination game. And it's possible to formulate the evolutionary dynamics of that kind of situation, of the coordination game. And what we get finally is this equation over here. It's the probability or relative frequency of showing behavior I at time t. And now what people are often interested in is what happens in the stationary state, in the equilibrium. So you set this to 0, the change to 0, and figure out, oh, there are 3 stationary solutions. One is p equal 1/2, one is p equals 0, and one is p equals 1. Then some people would do a stability analysis of those different stationary points. And the interesting thing is, the most natural behavior, like the 50-50 situation where you go in 50% of cases to the left and in 50% of cases to the right, the symmetrical behavior, that is unstable. So a little deviation from that will drive the system towards one of those other actually stable stationary states. And that establishes a behavioral convention. And it could be either the right-hand side or the left-hand side. It does not matter. The only thing that matters is that if all people start to do the same thing, it's perfectly coordinated. You don't have to enforce it. It happens by itself. So again, we can use that mechanism basically to establish coordination. We don't have to enforce it. Okay, and then I'm ending with a slide on swarm intelligence. And that's also pretty fascinating. And of course, there's a lot of coordination happening over here. Now, how do they do that? If that would happen at Schiphol Airport, I'm not sure you would take a plane at all. But birds can do that. And how can we use that? That will be part of my second talk about design for self-organization. But before I enter this, I'd like to ask, are there any questions or are there any comments on your side? Yes.
Thank you. Very interesting talk already, this first one. I'm curious for the next one. I have had a question about the phase diagram, and I was wondering, indeed, I mean, in physics we have phase diagrams for different substances, depending indeed on the substance. The temperature might change, the position of the points of the phases changes. Do you expect that that theoretical diagram that you have shown might change based on the different road segment that you are looking at? What would be the equivalent of different substances in traffic, in your opinion?
All right, a very good question. So, as I said, this was for a freeway with one on-ramp. You can extend the analysis to freeways with an on-ramp and an off-ramp, or with several on and off-ramps, and then you get more and more complicated kind of situations. The paper I've shown in this connection discusses quite a bit of that. It also shows that depending on the instability diagram of the traffic model, and that may depend on actually the driving parameters of the cars. You would get different phase diagrams. And as a result, also, some of those congestion patterns may occur or not. Or there may be additional congestion phenomena even. So it's a very interesting area to work on. So perhaps you'd like to take a closer look of this.
Be based on the driving style of the people. So depending on the city where you might look at the data, you might have a different phase diagram. Even.
Right. Driving parameters do matter. Yes.
Thank you.
And there was the second question right over there.
Thank you for your talk. And I have a question about the predictability you have, this term you have mentioned. And predictability sometimes is also being referred in the AI field. So in your case, I'm wondering if there's do you have any opinion on how to increase or improve such a predictability? And also you mentioned that there's some data that cannot be processed by the model or the computational power, but if it's increasing. This dark data that's critical, and this is if it's so necessary to process this dark data, and or to another word, if this dark data can be used, or if it's the dark data is critical to the predictability.
All right, it's a little bit like in astrophysics, where you have dark matter and dark energy, and by now, most people in that field think it's actually the majority of matter and energy. So, how much can you understand if the majority is hidden? Will we be ever able to process all the data? I'm not sure. Do we even want this? I'm not sure. Because I'm arguing what we should be aiming for is not total control of those complex dynamical systems, but fostering self-organization. So in principle, in that, what I often see in data analytics is people take a data set, they look for patterns, they find something, But then the question is, what does it mean? How does this pattern come about? How to interpret it? And what are the policy implications of that? And there can be many mistakes on that way. And the answer may be hidden in that, dark data. If you would look into that data, you might find the answer. However, also the question is, how would you have to look at the data? I mean, what kind of algorithm do you need to use? There's no universal algorithm that basically gives answers to all questions. So again, you have a complexity problem, and there's a computational complexity as well that we need to consider. Basically, it means that if you have computational complexity such as NP hardness, which applies even to traffic light control in cities, then you cannot basically find the answer in real time. Not in an automated way. And I would think it's actually good news for you, because it means you won't be replaceable by an algorithm. It still needs scientists really to get an understanding of these kind of systems, right? Otherwise, we would all lose our jobs eventually. So dark data could be a good thing.